forest canopy and changes in forest canopy that lead to an invasive species, and we'll talk about invasive species later, but its responses within the forest and thinking about how it was responding to changes in light. And so this was a gap that had formed that has this big open area, letting lots of light in as the sun passes over. Changing then what can grow underneath, because now we have this lots of light being used by what's growing underneath the forest. We've already talked about physiography, because we had glaciation, and so we've got these till plains, we've got the moraines that form, we have the ridge valleys that form in southern Indiana and into Kentucky. Physiography is just the landform. It's just the shape of the land and what that is going to do to the plants that grow there. So on this photo, we've got physiography. We've got a slope, we've got a ridge and valley kind of formed. And then the shade, we've got ferns. But in the sun on the opposite side of that little valley, it's bare. Why? What's going on there that would create this different groups of the plants growing on one side but not the other?
Southern facing?
Yeah, so we're going to have a southern face, which is the sunny side. We've got north face that's shaded. This may be turned a little bit. That may be slightly southwest. I can't remember where this photo is from. But yes, but why? What's going on the south facing where there's no plants? Or they've got individual trees but nothing dense? It's drier. It's hotter. So again, environmental conditions defining where the plants are growing. It's too hot, it's too dry. On the south or on the north facing slope, it's cooler, it's wetter. And so we get all these ferns taking up and starting the process of becoming a forest, which is then going to determine soil. And I put 3 exclamation points on the important role, because the forest is going to create the soil, that creates the forest, that creates the soil, that creates the forest. It's this back and forth interaction that connects everything together. So the soil is the connecting medium for everything that's alive, everything that's not alive, functioning as a forest. And we're going to spend some time on soil here in a bit. Oh, we're going to do it now. So, soils are so important to defining the forest. We have to take a step back and talk about what are soils. So what is soil? What is soil?
It's all the stuff that's decomposed and all the...
So we got stuff that's decomposing.
All the poop and grass from everything.
Waste products from everything that's alive.
Erosion of rock.
Erosion of rock. So dirt. So I took a soils class when I was an undergraduate, and my professor said that when it's in the ground, it's soil. The moment you take a shovel and turn it out, it's dirt.
Is that
Because
not fish tail?
no, it was that it would have been Hugh Brown.
Oh, yeah.
Yeah,
Okay.
he always said he had a colorful name.
Yeah.
But yeah, that was the idea though, is that when it's in the ground, it's everything that makes up and defines the soil. But the moment you turn it out with a shovel, you've taken out air and water and restructured it, and it's no longer soil. It's now flattened. It's now mixed rock. It's now upside down. It's everything that is not soil anymore. So soils are going to be the weathered rock. It's going to be everything that's dead and decomposing. It's going to be the waste products of all the animals being there. It's going to be water. It's going to be air. And the formation of that is all influenced by the parent material, which are the rocks. We'll talk more in depth about all this. But the parent material is the starting point, the rock starting point. So what is our parent material around here?
Limestone.
If we were in Bedford, Indiana, what would our parent material be?
Limestone.
Limestone. Here, though,
Decomposed.
it's the glacial till It's the moraines that formed. It's the stuff that the glaciers left behind. That is our parent material for most of our soils, which becomes clay and has some other things in it. But it doesn't have to be clay because there's sand in Fort Wayne as well. And so it depends on where that parent material came from, defines how the soil can develop then. And then we have climate still. We have to think about our humid, temperate climate that is creating the soil that we have here. And again, since that climate is great for growing plants, what it ends up doing is it creates soil that also is great for growing plants. Everything that's alive in that soil. So earthworms, beetles, turtles, snakes that are burrowing, those are all parts of the soil. And they are influencing how the soil forms. Topography, so physiography is going to play into it. As we have erosion, as we have pooling of water and soil in the valleys, the ridge tops get kind of washed away. All of that is defining what type of soil develops in each place. And then time. Time is another component that it takes a long time for soil to develop. When we have water, it develops faster. When we're talking about the West and it's drier, then it takes a lot longer for soil to develop. So time is a component, but it's related to everything else because they are not additive. Every single one of these influencing factors is interacting with the other to create the soil. And it's not just that time gets added onto topography, onto the organisms, onto climate, and onto parent. It's all the interactions that happen in all directions that creates the soil. Just like it's all the stuff working as a forest that creates the forest, the soil is one part that's leading to the forest. All right, so parent material. Again, we've got this glacial till, which is basically everything that got bulldozed by the glacier as it moves south. As it recedes, it starts dropping stuff, and that becomes our parent material for soil development. In southern Indiana, it's a lot of limestone. If we had volcanic activity, we would have volcanic rock that's creating that material. And so you can see we've got soil on the top, and we have parent material below that. And so what the parent material does through weathering, through breaking down, through becoming smaller and smaller pieces, that is its addition to the soil. It gives a lot of the physical characteristics of the soil. So how does water move through it? How does it hold nutrients? All of that is going to be related to the physical aspects of the soil, which are derived from the rock that started it. Also, pH, the nutrients, those are all coming from the parent material. So if we have a limestone soil, we're going to have lots of calcium. We're going to have lots of blue ash growing on that site. If we've got lots of glacial till, we end up with lots of clay. We get lots of nutrient-holding sites within the soil that hold on to stuff and keep it locked away from plants. So depending on what that soil parent material is how it's going to interact with the plants that grow above it in both chemical and the physical characteristics. So many of the nutrients that exist in the soil come from the parent material. A lot of the metals and some other really important nutrients for the plants are coming from the parent material where it breaks down. All right, so like I said, for us, we've got this glacier moving through. We have these till plains, and the till plains are basically the flat areas where the glacier kind of scoured everything and flattened it out. And then the moraines are the really big dropping points of rock and gravel and sand and clay, all that stuff that got picked up by the glacier gets kind of dropped in these ridge formations. And so we've got this Auburn complex and the Warsaw complex and the Kankakee drainage ways that are between the Valparaiso and the Plymouth complex. Basically these ridge valley formations, the big, large-scale ridge valley formations from the moraines that as the glacier kind of paused and dropped stuff and then kept moving and paused and dropped stuff. So the moraines are the leading edge of the glacier that's dropping things, especially as it starts to retreat.
What do you mean by dropping stuff?
Just what I mean is you've got a bulldozer that's pushing through.
Mm-hmm.
When it backs up, does it pull everything with it?
No,
No, it just kind of leaves stuff behind. Yeah.
But it doesn't back up, it just melts, right?
Melts.
Yeah, it's melting and moving. It's moving.
moves?
Yeah, there's movement
Is it
happening.
Like an ebb and flow. and
Yeah.
forward
It's more
and-
constricting than moving, right?
Yeah.
It's shrinking.
It's shrinking, yeah. So that's the movement happening, is the shrinking process. But as that front edge moves north, it's dropping what it was pushing before. Things that, and it's as it moves, it is holding things and is moving it forward.
Oh,
So that there's growth of
Like
the
an-
glacier.
like
There
an
is
okay,
movement
okay.
that is pushing it forward. And as the glacier then recedes, because it's shrinking, it's dropping what was held in the glacier on the front edge. And it basically is leaving ridges and heaps and piles and deposits as it's moving away from the site. So we would have had sands deposited. Then once that torrent, the Maumee torrent that let out Lake Maumee, then we get these big windstorms that are moving sand around after that lake has moved or is gone, and creating the sand dunes that exist in Fort Wayne. So the ridge through Fox Island is a sand deposit. It's an ancient dune that formed because there was deposits of sand as the glacier receded that it left behind. And that dune ridge goes into my neighborhood on the south side of Fort Wayne. And so I live in a neighborhood that has really sandy soils. I have giant pine trees in my front yard because that's that ridge that existed and formed from what was glacial deposits after Maumee had drained, and now we have this dry period, and we get these kind of mounds and dunes, or these dunes that form through the winds. Then we have also the till plains. These are the flat areas where we had detaching ice sheets that just sat in that place and melted. So we did have melting in place. We also had the shrinking and movement of the dune, of the glaciers away. And so in the till plains, that's where things just kind of sat and melted there. There would be deposits from the glacier there as well. They're not the same as the ridges that form from the moraines, but there is deposits within the till plain. Have you done geology yet? Or is that next? It's coming up next Saturday. Okay. Hopefully more in depth on the formation of plains and till plain, the till plains and the moraines as well. But that's where our parent material comes from. Up here is from the glacier, which means we have stuff that got moved from up north. So our formation of our soil may not reflect our actual geologic past because the glacier moved stuff here. And then climate is going to play into how that parent material breaks down. So this is the weathering, the breaking down of that parent material to release smaller and smaller pieces of the parent material that then release the actual nutrients for the plants. It's a very long process. This is not something that happens quickly. Soil development is a very slow process determined by climate, and the hardiness map is basically a climate map. Essentially defining those boundaries of the environmental conditions for plants is also defining the water and temperature that leads to soil development. So weathering of the parent material is controlled by climate. If we look at tropical soils, they're really old, but they're nutrient and mineral poor. So they've existed for a really long time, and really the only place we're going to see something like that is like southern Florida. But if we go down through South America, those soils are really, really old, but all of the nutrients have been washed out because they have so much water. So the water's moving through, it's washing the soil. And so nothing is left behind for the plants. If we look at temperate, like what we have here, we have decomposition, and we have lots of minerals from the parent material creating soils that do well for plant growth. And then we have the organisms on top of that, because again, stuff has to get into that soil. So this is going to be plant roots, but it's also any invertebrates that are crawling through the soil that are helping with decomposition, detritivores that are mixing that, adding nutrients to the soil. So we've already kind of talked about what are the biotic components, but basically it's anything that was or has been alive. So the dead stuff, things that are decomposing are part of that biotic component. Earthworms moving through are helping mix both the biotic and abiotic. So the parent material is abiotic, it's not alive, but the dead raccoon that's decomposing is biotic and is adding nutrients back to the soil. So we've got the living parts that are mixing. It's altering how nutrients are available because they're feeding. So earthworms are feeding, and then their castings, their waste is adding nutrients back to the soil. Organisms are going to add to how well can that soil hold water, and how well can it drain and add oxygen. So even though the roots are underground, they need oxygen. And if it's saturated because it's flooded and there's no drainage, there's a lot of plants that cannot survive in that because there's no oxygen. So plants as living organisms still need oxygen. Topography, like I said, we've got erosion on the tops of these ridges. That's basically moving soil down into the valleys. Flat areas are going to oftentimes accumulate soil faster than they can erode, but the ridge tops that are really sharp are going to lose soil through erosion very quickly down into the valleys where we get deposits. So we're going to see, if we move across a ridge valley pattern, we're going to see thin soils on the ridge top, and then as we go down the slope into the valley, it gets deeper and deeper soils, and as we come back up the ridge, it's going to get thin again. So different plants are going to be able to live in that, and that's why we're going to see drier soils up on the ridge because they're thin. We'll see wetter soils down in the valleys because they're really thick and can hold lots of water, which are going to then define the forest that can be there. And then time. Again, time is really important because soil development is really slow. So these are roads through the west. I think these might be in Utah. I can't remember where these are at. But these are roads that are no longer used, but still are visible because the soil hasn't grown up and the plants can't colonize what's not soil. So those tracks where the wheels from wagon trains move through destroyed the soil, and because it's so dry, it's an even longer time for the soil to rebuild. And so even after a couple hundred years, it's not enough time for soil to develop. Here, that may be very different. We'd see soil development in that time and start seeing plants colonizing it. But because it's such a dry climate, and again, it's that interaction. They're not additive, they're interacting. So time and climate lead to a really slow development of the soil. So depending on the climate, it can be thousands of years to get soil developed. It's all weathering of the parent material, decomposition of organic material. So anything that was alive decomposing is going to play into that. And if it's really dry, there's not enough water for decomposition, and it starts to really slow things down. Okay. So from the parent material, like I said, you get both chemical and physical characteristics. So the physical characteristics are things like texture. And texture is just the size of the particles. So if we looked at sand particles from a sandy soil under the microscope, they're really big. If we look at clay particles under the microscope, they're flat and small. And so the physical arrangement of those particles is the physical characteristic of the soil. So it's how sandy, how silty, how clayey that soil is defining that physical texture. So sand particles are really big, and they're kind of irregularly shaped and roundish. And what that ends up doing is it creates big spaces between them. So water wants to move through, big air pockets in the soil that's sandy. Clay, they're really small particles and they're flat, they stack up, which ends up meaning that water can't move through them. So in a field that has lots of clay, right now, what does it look like? They look like ponds
It's like my backyard.
because they can't drain because the particles are so small and tightly packed. Silt is kind of in between on the sizes and different shapes and sizes and can add to drainage and aeration. And what we end up finding is that those loamy soils where we have a balance between clay, silt, and sand, those become the best places for plants. And that's, what's that?
Is that what loam means?
Honestly, I don't know what it actually means, but yeah, it's the balance between them. And so we get drainage, but we also get water holding capacity. We get nutrients that are available, but we also get the holding of nutrients back. And so basically the goal for agriculture is to find the most loamy soils because they have a mixture of everything. But those are also the best places for our forests around here are on those loamy soils because they're the mixture of all the physical characteristics of the particles. And again, the physical characteristic is going to influence nutrients and water availability to plants. Yeah.
I had a question because I learned way back, that the prairies have the best soil for, that the grasses have the best soil for agriculture as opposed to the trees and forests.
So what we're going to see is that, yeah, grasslands are going to be more loamy, but also climate plays into it. Some of our areas start getting into the clay loams, especially around here. But yeah, so prairies do have really good soils. The problem is there's a lot of complications with using prairies as agriculture
Okay,
in
because
terms
I
of the
thought-
regeneration of the soil.
I thought I'd heard that once they started cutting down the trees for agriculture, that they had to keep doing it because they were only able to use it for so many years, and then it was.
Well, yeah, there's a whole range of complications with row crop agriculture to begin with. So, yeah. Chemical characteristics. pH is really important.
pH,
This is the, what's that?
what's pH?
It's the inverse log of the percent of hydrogen ions that are available. So it's basically, is it acidic, is it alkaline?
Okay.
And is it neutral in the middle? So neutral is 7. If it's below 7, then it's acidic. If it's above 7, it's alkaline. It's basically just a measure of how acidic or alkaline the soil is. Neutral is great because it's balancing kind of the available nutrients. But as we start getting into really acidic soils, we get more nutrients, but we oftentimes see more metals. When we go to alkaline soils, they're locking away nutrients because of that interaction with pH. But it all comes from the parent material, and there's some acids that are coming from decomposition. So there are organic acids that get released that help with releasing nutrients in the soil. So there's a whole chemical side of things that is the interaction with plants in the soil. So pH changes the availability of nutrients. Like I said, really acidic soils, nutrients get released really, really fast. And as water moves down, it starts to wash those nutrients out of the soil. And then it also will release metals which become toxic. So aluminum and copper are needed in really, really small amounts, but as the acidity of the soil goes up and it gets more and more acid soil, those metals become available and they become toxic to the plants. So, anybody know where that photo's from? No, not Yellowstone. I've already talked about it. What's that? It's the Smokies. So that's Smoky Mountains. So this is a spruce fir forest. What do you think happened to the spruce fir forest?
That beetle that's going through?
The beetle probably, there were probably beetles involved, but initiating this.
Was that the fire?
As
No, it's acid rain. It's acid rain deposition from the southeast. So basically we get a whole range of industry and coal-fired power plants and lots of acid going into the atmosphere, being deposited in acid rain. So not only is the acid hurting the leaves, the needles of the trees, but then it's altering the soil. And so the metals that are in the soil start to become toxic to the plants, and the tree dies because of metal toxicity. The acids aren't killing the leaves and stripping out everything from above ground, it's everything happening below ground. There are still trees coming up underneath recovering from this, but even in the background you can see all of this kind of whitish. There's tons of dead trees back there as well. It's all from acid rain deposition.
And that's recent still? I thought it was in the 80s.
This photo's not that old, but it's better than it used to be, but it still exists. There's still acid rain that alters the soil chemistry. So as the soil develops, we get this layering pattern that exists underground. What we see on the top, that is stuff that we can identify. So if you pick up a leaf and you say that's an oak leaf. If you pick up a raccoon, you can say that's still a raccoon. It's the organic layer. So if you can identify what it is, it's part of the O horizon. And we call them horizons, it's the layers. So the O horizon is this organic layer, especially stuff that we can identify. Below that we have the A horizon, which is decomposed organic materials. The stuff has decomposed and has moved down through the soil by water. Nutrients are there. That's where most of the plant roots are, is the A horizon. But after we move out of the O into the A, you might be able to say this is really organic because it's dark, but you can't identify necessarily what it was. It's just everything that has decomposed that has now become part of the soil. Below that we have B, which is partially weathered, or it's weathered parent material. It's a transitional layer between A and C is the unweathered parent material. Again, plant roots are almost all in A. Big trees will have roots that extend down into B, but most plants have roots only in the A horizon, because that's where all the nutrients are. It's where all the stuff that is decomposed is available to the plants to take up with their roots. That's where most of the water is as well. There's some in B, but A is where all the stuff the plants are wanting is located in the A. So, coming back to what you said about prairies, depending on the plant community that we're looking at will determine how deep the A horizon is and how thick the O horizon is. And so if we've got a pine forest here on the left, there's a color change about right here at about probably about 50 centimeters or so into the soil. So the O is at the top where we can still see pine needles and branches and things, but below that's our A horizon. Compare that to the grassland, which is over a meter, so 110 centimeters or so deep. So twice as much of A horizon deep compared to the pine forest. So that's why, you get a lot of plant roots down into the A. We get this development of a really thick A, which makes it really great for agriculture, but it can't sustain continuous use because it's so thick and it's so dependent on the grasses up top that we're creating it. And then a hardwood forest, the units are different. Now we're in feet. It's about a foot deep, and it's comparable to the pine. The difference is the thickness of the O is going to be different. And oftentimes what we're going to see is a little bit thinner in the hardwood forest of an O, a thicker O in the pine. The pines are going to have a higher acidity, so the decomposing pine needles are adding to the pH of the soil that's determined by the parent material. So they've got this interaction with what was growing there before, creating and influencing the soil below it. But very different patterns. In this one, it's harder to see the transition, but there is kind of a color transition at about a foot or 11 inches or so in the hardwood forest.
And why would the hardwood have a thicker O than the pine?
The pines usually have a thicker O,
Oh, the pines are.
because the acidity alters how quickly the fungi and bacteria can decompose things. So it builds up into this thick duff layer is what it's called, where it's still pine needles.
Because I would think that the deciduous trees, since they lose their leaves every year, would have more.
But there's a balance in the pH oftentimes, and so decomposition happens at a relatively higher rate than the pines. Things like oaks that have a lot of tannins and higher acidity sometimes slow down, but everything else decomposes pretty well in a hardwood forest. If it didn't decompose, it would start really building up, and the pine layers, they usually have a really thick layer of needles underneath. All right. It's almost 8. Do we need another stand-up break? Are we good? Pressing on. We're going to go to something completely different now. Still related to forests, but a very different concept with plant succession. We good? Okay. All right. So again, we've talked about forests in general. We talked about Indiana, forests where they came from. We've talked about how the environment and the soil basically influence the forests that exist there.